Can you see my screen?
Yes.
Yes.
Okay. Okay. So last time we discussed about characters. So we saw the definition of a character of a representation, which is basically you take the trace of rho G, where rho is the representation and G, little g, is a element of the group. Yeah. So it's a function from G to the base field. Since we are working over complex numbers, the range will be complex numbers. Yeah. So it's a function, and as we will see that it more or less determines the representation as well. So in fact, if your representation is one-dimensional, of course, character is same as the representation. So there, of course, it determines. But in general, it's an invariant. Yeah. So some things is easy. So we saw some properties of character. For instance, the dimension of the representation you can easily read out. Just look at its evaluation at 1, evaluation of the character at 1, and that is the dimension of the representation. The character of G inverse, the character function, if you evaluate it at G inverse, that is same as the conjugate of character function evaluated at G. And the third one was that it's a class function. So it is constant on a equivalence class. Yeah. So character of G inverse HG, a character evaluated at G inverse HG is same as character evaluated at H. And so the proofs were not that difficult. Just look at eigenvalues and so on. Yeah. And then just by definition, by looking at how the representations look like, we notice that character of this representation, if V and W are representations, then the character of V plus W is just character of V plus character of W. And character of V tensor W is character of V times character of W. And then there was another representation which I should have mentioned here, maybe two of them. Yeah. So let's just extend this to the other two. So let's see, what is the character of V dual? So if V is a representation, we know there is a dual representation. So what will be character function for the dual representation in terms of the actual representation?
It will be the same.
Say that again.
It will be the same.
And yeah, so it won't. No, it won't. So how does the dual representation look like? So what is rho V star G? So in terms of matrices. So think about in terms of matrices. Yeah. So if we fix a basis and the dual basis, we saw this in last time. Yeah. So the matrix is you take the inverse and then take the transpose. Yeah. If A, so recall that rho V star G with respect to the dual basis is, and if this is given in some basis, is same as rho VG inverse transpose in matrix representation. Yeah, matrix representation. So if you want to take the trace of rho V star G, then that is same as taking the trace of this. Yeah, but what is the trace of this guy? So transpose you can forget, yeah, because transpose doesn't change the trace. So what is the trace of inverse matrix? So here we know what I mean. So the eigenvalue. So I mean the matrix is so you can write it in terms of eigenvalues. Yeah. So matrix is diagonalizable in all these cases, yeah, because by the way, this we used last time as well, but I didn't maybe say it explicitly. Yeah? So why is the matrix diagonalizable? Why is this rho VG diagonalizable in our setup? So once you know it's complex numbers, so that but not every matrix over complex numbers is diagonalizable. What condition do you need? So of course, if you take this matrix 0, 0, 0, 1, then this is not diagonalizable, right?
But it's not invertible.
So invertibility is not an issue. I can put 1, 1 here. Yeah, now it is invertible, but this is also not diagonalizable. Yeah, so you have a Jordan block like this, then it won't be diagonalizable. So there are complex matrices which are not diagonalizable, just in case you thought that way. Yeah. So what is the condition for diagonalizability?
It splits into linear factors instead.
What splits into linear factors?
The minimal polynomial.
Minimal polynomial, yeah, precisely. So if the minimal polynomial is product of linear factors, then you can say that it is diagonalizable. So what is the minimal polynomial here? It's going to be a factor of x power size of g minus 1, yeah, because we know that the image is going to be some matrix whose nth power has to be identity, yeah, for some n. And of course, x power n minus 1 has has no repeated roots. Yeah, so it's product of distinct linear factors. So not just distinct linear factors. Yeah, of course, over complex numbers, everything you can write it as product of linear factors, but the point is distinct linear factors. So minimal polynomials shouldn't have repeated roots. So if you see this one, this has repeated roots. Yeah, the minimal polynomial of this is going to be x minus 1 whole square. So of course it's linear factors, but not distinct. Yeah. So I'll remove all this remark and I put the notes. So that tells you that this matrix is indeed diagonalizable. And then of course you know that the inverse, the eigenvalues of the inverse is going to be the reciprocals of the eigenvalues of the original matrix, and hence but they are all of size 1. Yeah, so norm 1. So it's the conjugate. Yeah, so that tells you that this is chi v bar. Yeah, you just have to do chi v bar. So maybe I'll give you, so maybe I should write something here. So chi v star g is trace of rho v star g, which is trace of rho v g inverse transpose, but maybe transpose I'll just remove because since this happens, yeah, which is same as summation lambda I inverse I equals 1 to n, where what else? Maybe I'll not write the range of the summation. I could, but let's just say summation lambda I, where lambda i's are eigenvalues of rho vg. Yeah. So the point is the eigenvalues of rho vg inverse is lambda I inverse in this case, and but lambda I inverse is same as lambda I bar, which is lambda I bar, and this is since lambda I norm is 1. Yeah. So it is chi v bar. So the dual has, so the dual character is just taking the conjugate. Yeah? So it's easy to write down the dual character as well. Okay, and then what about, so what was the last thing? So we have tensor product, dual, and then there is home. Yeah, so what is the character of, so we can also cook up, ask what is the character of home VW. Yeah, because this is also a representation we saw. Yeah. So what will be the character of this guy in terms of, yeah?
So am I audible?
Yes, tell me.
Yes, sir, could you please just scroll once to the top of the page? There was some internet problem over here and I could not see your screen.
Top of the page.
Yes, sir.
Yeah. This one?
Yes, sir. Like whenever we started, the first part on screen was frozen for some time.
So sorry. So is it okay now?
Yes, sir, it is okay.
Maybe your connection might be, yeah.
Yes, sir, there was a problem over here.
So it is just definition of character and then the proposition we proved. And then a few remarks which someone mentioned, so I don't remember. Maybe it was Soham about these two. And then this dual also we could have talked about yesterday itself, but this is there. So what is the character of the dual representation? Finally, what is the character of home VW in terms of V and W? Any guesses?
So we can use that breaking part, like over here, the home VW can be broken into two parts. Right?
What is the breaking part?
So V star tensor W.
So that identification we can use. Yeah, very good. So this is going to be, and this is same as chi of V dual tensor W, since home, since we this maybe I left it as a homework problem. Yeah, as G representations, they are same. Yeah, so this is as representations. Okay, and now we know. Yeah, so now you use C and B to say that this is same as chi V star, but that is same as chi V bar plus chi W. Okay. So we know, so whatever objects we have created so far from representations, so we know how to compute them. Compute the character for all this. Yeah.
That will be multiplied, right?
Say that again.
X.
Oh yeah, this is not plus. This should be product. You're right. Sorry. Plus is when we take the direct sum of representation. Product. Yeah, right. Good. Yeah. So more or less we know how to calculate character in most of the examples we have seen. Yeah. So if you have if it's one dimensional, then we know how to do it. If it is sum of representations and so on, we can do it. Yeah. And so even for tensor algebra, we can do it. Yeah. So there are a few things missing. So for instance, what will be the character for the symmetric algebra? Yeah, so what will be the character for the tensor algebra? So from here we can just say, maybe let's call it E, yeah, T and V. So this is just a consequence of the previous thing. This is just chi for n, yeah, chi V for n. Right? Because you have two of them, you just have to do squares, and if there are many, then you have to do this. Yeah. So we'll talk about the exterior and the symmetric as well, at least the degree 2 one, yeah, because there the basis is very explicit, and the remaining one you can do it for fun. But before that, there is one more representation which we studied, yeah, regular representation. So maybe we'll do that first and then come to the exterior and the at least the symmetric 2 and the exterior 2. So let G be a finite group. And then kg v equals kg is a regular is a regular representation. So we know what how the action is, yeah. So you think of it as linear combinations of elements of G, and then the action is pretty straightforward. You can also think of it as functions from G to K, and then the action is somewhat different, yeah. But it doesn't matter. They are both isomorphic. That was also a homework problem, I think. Or I'll put it as homework if it wasn't. I think this I have assigned it as a from BMathIII. No, not BMathIII. Yeah, Fulton Harris. Yeah. Okay. But anyway, so we want to know what is character of V. Yeah. So so it actually does not depend on G. If you're meaning. So at least some element we know, right? So if you consider the identity element, what is this? What will be the number?
1.
No.
Mod G.
Size of G. It's the dimension of the representation. Yeah. So it's size of G. That we know. Yeah. Now suppose G is not, you take G in G such that G is not the identity. G not equal to 1. Then what is chi G? Chi V of G?
So it will be 0 because there is no fixed point.
Yeah, so what does it have to do with fixed point? Yeah, so
basically it's a permutation, so the diagonal would be 0.
Yeah, so you think in terms of how, so you have to think in terms of the matrix. Yeah, so you fix a basis. So anyway you want to compute a trace, then it's a good idea to write a matrix. Yeah, and there is a natural basis which is basically elements of G. Yeah, of this guy of this vector space. And we know that G and we know how this works out. Yeah, so it is a permutation representation. So when we were discussing this the first time, I told you that this is a special case of permutation. So with respect to this matrix, with respect to this basis, where your basis elements are elements of G, this is a permutation matrix. Yeah. And then you know what the trace of a permutation matrix. Permutation matrix have only ones and zeros, right? And it has and each row has exactly 1 1 and rest are zeros, and each column has also exactly 1. And so you just have to look at the trace of this permutation matrix, and it will have a 1 in the diagonal only if it is if this permutation fixes that element. Yeah. So this G, G acts on G via, let's say, left multiplication. Yeah. So this action will give a map from G to let's say symmetries of G. So meaning permutations of G, yeah, bijections of G, which sends G to some sigma G. Yeah, sigma G is the permutation G induces after left multiplication. So sigma G is a map from G to G. And what is this map? It sends H to GH. Yeah. And what are the fixed points of sigma G? There are none, right? Because if you think about it, you want fixed points means GH should be equal to H. But GH is equal, so sigma G of H is equal to H implies GH is equal to H, which implies G is equal to identity. Yeah. Hence, if G is not equal to identity, then sigma G H is not equal to H for all H in G. Yeah, so there are no fixed points. So that means there will be no entry in the diagonal, which will be 0. Yeah, so with respect to the basis 1 G in G of V, which is same as Kg, by the way. Rho V of G is a permutation matrix whose diagonal entries are 0. So it's going to be a permutation matrix, and this the action is such that it doesn't have any fixed points. So the diagonal entries are all 0. Yeah. So that tells you that the trace hence trace of rho Vg is 0. Hence, chi Vg is 0 for all G not equal to 1. And for 1, we know what the answer is. Okay. So computing the character of the regular representation is pretty straightforward. Yeah. It is just for 1, it is the dimension of the group, is the size of the group, and for the rest, it is 0. So it's very easy. Similarly, if you are given any permutation representation, so if you have an action of G on a set X and you consider the corresponding permutation representation, that is, you take a vector space generated by elements of X and the representation induced by that. Then also computing the character would be same as computing the fixed number of fixed points of that action. So if you are given an action of a group G on a set X such that you can compute the set of all fixed points, then that's it. Then it is straightforward to compute the character. Yeah. So maybe I can write down the statement more generally and and the proof is same. Yeah. Let X be a G set and rho from G to Vx be the permutation representation. So G set means there is action of G on X, and then the corresponding permutation representation, we know what it is. Yeah. Then chi of Vx at G is the number of fixed points of sigma G, where sigma G from X to X is given by X going to G dot X. Yeah, so it's X is a G set, so there is an action. Yeah, so that induces this. So I don't know how you want to. So it's basically the fixed point of the action. Yeah. So you want to think of whatever way. So a fixed point of a function, you know. So that's why I've written it in this way. Okay. So fixed points of the action also you can define it as fixed points of sigma G. Okay, so this is for a general set. Okay. So if G is identity, you know this everything will be fixed. So this is the size of X. But if G is not identity, then it depends. Yeah. And that's it. So you get a formula for permutation representation, and the proof is same. Yeah. So that is how we prove this this representation. Okay. Any questions so far? Okay. So let me do this exterior and symmetric power, and then we will go to Schur's lemma. Okay. So same. So maybe the general one might not be too bad, but I don't want to, because sim2 is easier to do. Yeah, so I'll just stick to this. Yeah? So sim2v, we want to, so this is also a representation. Yeah. And we want to say that this is, we want to compute the character of this. Yeah. So I want to think of it as a sub of tensor. So we know that this is both quotient and sub of tensor. Yeah. So how do we think of it as sub of T2V? So the idea was to consider. Yeah. Yeah, so how do we, so the basis element, so if, we'll work with basis, yeah, so let V has basis E1 to En, yeah, then here the bases are Ei dot Ej, yeah, and the inclusion map which we sent was something like E1 tensor Ej minus plus E2 Ei tensor Ej plus Ej tensor Ei. Yeah, this is how we define this E map. Yeah, so if it was general, then we took the sum over all possible permutations. Okay. And then we showed that this is an inclusion, and then your homework problem was to show that this is the equivariant, right? Similarly, you have a map from X to V to T to V, and for 2 this is so Ei wedge Ej. So these forms a basis if I is different from J. Here I and J could be same. Yes, to E1 tensor E2 minus E2 tensor E1. So if there are more guys, then you have to worry about sign, etc. So it becomes slightly more complicated. But here the formula is nicer. Yeah. So in fact, these form a basis. Yeah. So note EI EJ I less equals J is a basis of sim2V, and EI wedge EJ I strictly less than J is a basis of X2V. And in fact, we know that the direct sum is whole of T2V. Yeah? Moreover, so what we can say is that moreover, yeah. So let me just write this down. Moreover, sim2V direct sum X2V under these maps. Yeah. So using these two maps gives you a isomorphism. This induces a isomorphism of T2V. So let's call this I1 and I2. Yeah, so this is I1 plus I2 map. This induces an isomorphism. Yeah. So this is which is G equivariant. So this is from the homework. Yeah. Homework problem. So this is equivariant was homework earlier, and G equivariant is homework later. Yeah. So that tells you that this is a this implies EI tensor EJ plus EJ tensor EI I less equals J union E1 tensor E2 minus EI. I don't know why I shifted to two variables. I mean, I shifted to 1 and 2 instead. EI tensor EJ minus EJ tensor EI I strictly less than J. Yeah. So this union, the previous statement implies that this is a basis of E2V. Yeah. So to compute traces, we can use this basis as well. Yeah. So let's try to understand how the action works on this using this basis. Yeah. So what is G of G dot E1 EI tensor EJ plus EJ tensor EI is? This is same as G dot EI tensor G dot EJ plus G EJ tensor GEI. Yeah. Yeah. So what do I want to say? So I want to say that yeah. So yeah. So eventually one has to get down to eigenvalues. Yeah. So yeah. Yeah, so first of all, yeah, so yeah, so I'll take, I had choice of the basis, yeah, so I don't want to take an arbitrary basis. I want to take a basis which which form an eigenvectors of G, yeah. So let's suppose, so now assume E1 to En as eigenvectors. So we can do that, yeah, vectors of rho G with eigenvalues. So that is easier to figure out this computation, lambda 1 to lambda. It's going to be some numbers. So then what I'm trying, so then this right hand side is going to be lambda I EI. So maybe lambda I lambda J. So it will come out to be lambda I lambda J times the vector you started with, EI tensor EJ plus EJ tensor EI. Yeah. So that tells you that, so if E1 to En are eigenvectors of this, then these are eigenvectors of G action on symmetric. Yeah. So that tells you that chi G of sim 2V is going to be summation lambda I lambda J I less than J. Yeah. Less equals J. Which I can write it as, so now I want to express it in terms of V, right? So this I can write it as, summation lambda I whole square, but I have to subtract something, yeah? So if I do whole square, then there is, so that is same as summation lambda I lambda J with no restriction on I and J. But here there is some restriction. So this is minus summation lambda I lambda J J strictly greater than I, yeah, because less equals we want those which are for which is less equals is there, yeah. So that is what we get, yeah. So this part is chi V G whole square, and this part we still have to understand, yeah. So this maybe is in terms of X, J greater than I lambda J. Okay. So now let's look, apply the same thing to, is it making sense so far? Yeah, so I'm trying to do the calculation. So this is just some calculation, yeah. So now let's try to do work out for the other pieces in the basis. So G dot, so what I'm trying to do is identifying sim2V with the subspace, yeah. Because this is an equivalent map, I can identify with the subspace generated by EI tensor EJ plus EJ tensor EI, where I is less equal C. And X2V I'm identifying with this subspace, and I'm trying to now look at, so they are linear, they are disjoint, yeah, they are linearly disjoint. So the intersection is just identity, so because this direct sum is there, yeah. So now I'm trying to calculate on these pieces. They are sub-representations, and I'm just trying to calculate the character of these sub-representations. Yeah. So G dot E1 EI tensor EJ minus EJ tensor EI. Yeah, this of course the action is straightforward. It's GEI tensor GEJ on the tensor algebra, on the tensor power GEJ tensor GEI. And now since this is again eigenvectors, so this becomes lambda I lambda j again, and the same vector comes out. Yeah, so EI tensor EJ minus EJ tensor EI. So again, this basis happens to be a basis of eigenvectors for G action. Yeah, so that tells you that this implies that chi x2v, which is basically the sub-representation generated by these guys. Yeah, evaluated at G is some of the eigenvalues, and the eigenvalues are lambda I lambda j. Yeah, summation lambda I lambda j, I is strictly less than j, or j is strictly less than I. Both are same. Yeah, whichever you. So that is the other piece. Yeah, so that tells you that so that tells you that chi. So you get chi. So you get a formula for, so yeah, so I don't know if I've done, so so what I've proved is something which is which we knew already, but anyway, I think I've given you some formula as well. Yeah. So this piece, anyway, we knew that this sum has to be this whole guy. Yeah. So we got that chi of x2g is precisely this, which is so if lambda is eigenvalues of in G action on TV, then yeah, so this is what you get. Okay. So somehow I thought one could give a formula of chi G sim to V in terms of just chi G V, but that doesn't seem to coming out. No, it will come out. Yeah. So we get this. Yeah. Now this is yeah. So another way to interpret this is summation lambda I whole square. Yeah. Minus summation lambda I square by 2. Yeah. Is this okay? So what I'll do is so I not equal to j case is captured here. Yeah, summation lambda I whole square minus summation lambda I square is basically summation lambda I j, where I is different from j. So if you divide by 2, you get I is strictly less than j. Yeah, and this of course you can write it as okay. So this is character of Vg whole square minus this is character of so if this is same as character of G square. Yeah, G times G. Character of G is going to be summation lambda I, but G square will have eigenvalues lambda I square. Yeah, so this is precisely. Yeah. So and maybe you can get a formula for sim2v as well. Yeah. So once you have a formula for x2, you can automatically get by for sim2 in terms of this. But of course, you can directly as well get it. Yeah. So note also chi t2v is chi sim2v plus chi x to v. So you get the formulas directly. Okay. Is this okay? I hope it made sense. Yeah. Any questions or comments? So I've given you the formula for the character of x2 and sim2 just in terms of character of v. So for general, I don't know if this is possible. You have to do some combinatorics with respect to these guys for general sim. But yeah, you can check if you can get something like this for higher ends. Okay. Are you guys with me? I haven't heard anyone speak for.
Yes.
Yes. Okay, so I hope everything is obvious. That's why people are not saying. Okay, so let's. So this is all I wanted to talk about characters today. Let's move on to Schur's lemma. Yeah, so I want to prove the Schur's lemma today. So hopefully there's enough time for that. So let V to W be two irreducible G representation. So I made this statement, but I didn't write it down. And let F from V to W be a G equivariant. First, I just wrote equivariance. Be a G equivariant. Be a G equivariant map. Then F is either 0 or F is an isomorphism, meaning so if it is non-zero, then it has to be an isomorphism. So if it is isomorphism, you can identify W with V. Yeah. So moreover, if you think of W as V, then F has to be a scalar multiple. Yeah. So it's not some crazy F is not going to be some crazy element of GLN of V. If V and W are same, it's just the scalars. Okay. So it's pretty. There are no complicated G equivariance map between irreducible guys. Yeah? And hence between any two representation, it's just identifying some particular sub-representation in some sense or something like that, or killing something. Okay, so let's see a proof of this. So this is not at all difficult. It's more or less straightforward. Yeah. So let so F is a G equivariant map. So let V0. So F is also linear map. So you can talk about what is the kernel of F. Yeah. So let V0 be kernel of F. Yeah. So then what can we say about V0? V0 is also a sub-representation, right? Because this is a G equivariant map. Then V0 is a sub-representation. Sub-representation of V. So maybe let me since we didn't do this, let me give you an argument. Since if V belongs, so I have to show that if something is in V0 and if I apply G, then it remains in V0. So if V belongs to V0 and G belongs to G, then G dot V, when I apply F to it, this is same as since F is G equivariant, this is same as G dot F of V. As F is G equivariant, which is, but F of V is 0 because we had chosen something in the kernel, which is 0. So yeah, so that tells you that kernel is indeed a sub-representation of V, but V was irreducible. Yeah, but V is irreducible. So V0 is equal to 0 or V0 is equal to V. Yeah, it's either the trivial is either 0 or the whole thing. So this implies f is 0. Yeah. And if V is 0, V0 is 0, then f is injective. So it's still not an isomorphism yet, but for that we'll use, we only use so far V is irreducible. Yeah. What is image of V? So image of V, image of F rather, which is F of V, is a sub-representation of W. Of W. Since, so again you use since F is G equivalent. So again you use the same thing. If you take something in the image of V, in F of V, so let's call W is in F of V, then G dot W is same as G dot F of some little v, and G equivariance will tell you that this is same as F of G of little v, which is again in the image of F. Yeah, so it is a sub-representation, just using this. Hence, by irreducibility of W, image of F has to be whole of W. Yeah, because it can't be 0 unless V itself is 0. So if V is 0, then what? Yeah, then the map is 0. Yeah. So then we are in this the other setup. So we are assuming V is non-zero. Yeah. Yeah. V0 is 0, which is not equal to V. Yeah, so we are in this setup. So that which implies F is an isomorphism. Yeah. So that proves the first part of Schur's lemma, which was that F is either 0 or an isomorphism. The second part is if W equals V, then we want to show that F is a scalar multiple. Yeah. So now assume V is equal to W. Yeah. And so F is an endomorphism of V. F from V to V is an endomorphism. But if you have any endomorphism, then you also have a eigenvector, eigensubspace. Yeah. So let lambda be an eigenvalue. Value. So this is the standard trick value of F. Yeah. Then consider F minus lambda I. Yeah. From V to V. Right. So of course this is just a scalar multiple. So this is of course lambda times I is G equivariant, F is G equivariant. So this is G equivariant. Yeah, and this is trivial on and not an isomorphism, and not an isomorphism. Because it has a kernel, you take the eigenvector corresponding to lambda that will lie in the kernel. Yeah. So it's not an isomorphism. Hence, by the previous part, both V and V are irreducible. Hence, by previous argument, this part, F minus lambda is 0, which implies F is lambda times lambda I, maybe I should write identity. We will not think of in terms of matrices. We haven't fixed spaces. So that completes. This is what we wanted to prove, is scalar multiplication. Yeah. So make sense, everyone? Any questions or comments?
Actually, sir.
Yes.
Yes, sir. Over here, can we also directly say that the eigenspace is G stable over here?
Yeah, eigenspace will be G stable. That
Yes.
is also true.
Yes, and it's non-empty, so it has to be V.
Yeah. So yeah. So irreducible. Yeah, you can just so you have to give an argument that the eigenspace is non-G stable, but it's the same argument. Yeah, equivariant.
Yes,
you have to use F is equivariant. Yeah.
Yes, sir.
To argue. So yeah. So you can argue G stable. Yeah. So it's similar to saying that kernel is kernel. So it's more or less the same argument as kernel is G equivariant subspace.
Yes.
So actually, that is what we are saying. Yeah. So it's okay. So either, yeah. Any other questions or comments? Good. So maybe I'll stop recording. Did I stop recording? No.